In the last video, we looked at a formula for getting the perpendicular distance of a point to a line. In this video, we're going to try and prove this formula for the general case. But first of all, we're going to look at a specific case. And we're going to follow the method for proving this formula for the line y equals x plus 2 and the point 7, 3. So the distance of 7, 3 to the line is d. We are going to find d by considering this right angle triangle. We're going to look at the horizontal distance of the point 7, 3 to the line. Let's see how to get this horizontal distance. Well, we know that the y value of this point is 3, and the y value of this point is also 3, because the line is horizontal. So what we need to do is to find the x value of this point. Well, you can see from the diagram that x equals 1, but in general, what we have to do is use the equation of the line. We see that y equals 3 for this point. So it's just the y value of the point in question. You know, this point is normally labelled x1, y1 when we use our formula. So you can see that the y value for this point here is also y1. So that's something to keep in mind when we prove the general case. Anyway, y is 3, so how do we find x? Well, we just sub it in here. So we replace y with 3. 3 must equal x plus 2 in our equation. So we see straight away that x is 1. So that's how we find the coordinates of this point here. So now we can find the length of this line. It's just a matter of subtracting the x coordinates of these 2 points. 7 minus 1 is 6. So this distance here is 6. So we have a side of this right angle triangle. The next thing we need is an angle, and we can find that too from the equation. We can find this angle here from the equation. I will call this angle capital M. This angle is the same as this angle here. These two angles are called corresponding angles because the green line and the x-axis are parallel to each other, and the red line cuts across these two parallel lines to make corresponding angles. Now, it's a fact that the tan of an angle that a line makes with the positive x-axis is equal to the slope of a line, and that's very easy to see for the case of a line with positive slope. So we'll just do this simpler case first. We can see that this line makes an acute angle, that is an angle less than 90 degrees with the positive x-axis. So the tan of this angle will be positive, the slope will come out to be positive. So we can get the slope from the equation of the line. If we have the slope, then we have this angle M, and we have enough information to solve this triangle and find D. Well, we just have to get our line in the form y equals mx plus c. And we can just read off the slope. We can see that the coefficient of x is 1, so the slope of this line is 1. We can also see it just by looking at the diagram. The tan of M is the side opposite M. Say we're looking at this right angle triangle here, formed by the two axes. Then the side opposite M is 2 units long, the side adjacent to M is 2 units long in this right angle triangle, so the tan of M is opposite over adjacent. 2 over 2 is 1. So it's easy to see when M is an acute angle, so the line will have positive slope. So we get that M is 45 degrees, inverse tan of 1. So to find D, we just have to use some simple trigonometry. We can see that from this right angle triangle here, I'm just reproducing this, sine of 45 degrees is the side opposite 45 degrees, which we're calling D, what we want, divided by the hypotenuse of this right angle triangle, which is actually 6. The longest side is 6. So D then is just 6 sine 45. Sine 45 is 1 over root 2, so to 2 decimal places we find that D is 4.24. Now let's look at the general case. we have our line in the form ax plus by plus c equals naught. Now, first of all, I will consider the situation where the line has positive slope. In other words, the angle between the positive x-axis and the line is an acute angle, an angle between 0 and 90 degrees. To find d, we need the coordinates of this point, just like you saw in the last example. We know that this line is a horizontal line, so we know that its y value is y1. So we have to find its x value. Well, it's a point on the line with this equation, so we sub y1 into this equation to find out what x is, to find the x value of this point. So this is what we get when we let y equal y1. So we need to rearrange this to find out what x is. So x is going to be minus b over a times y1 minus c over a. Of course, we're assuming here that a is not 0, so that we can divide across by a. If a is 0, then we have a line of the form y equals a constant. A line of the form y equals a constant is a horizontal line. And that's a separate type of situation that we won't deal with. Okay, so we can now write in the coordinates of this point. So now we can write in the horizontal distance between x1, y1 and the line. We just take x1, the x value of this point, and subtract the x value of this point. So we have x1 minus all of this here. So we get this. Notice that for this situation, x1 is greater than minus b over a, y1 minus c over a. The x value of this point is to the right of the x value of this point. So when we do subtraction, we get something positive. So this quantity is actually positive. Of course, in other situations, this quantity could be negative. If we had a point on the other side of the line, and we're looking for the perpendicular distance, then the horizontal distance would be like this. So the x value of this point would be x1. The x value of this point would have this form here. So if we do the subtraction, we will get something negative if we use this quantity, because x1 will be less than the x value of this point. So in order to avoid problems with signs, it's best to take the magnitude of this quantity. So the magnitude will always be positive, regardless of where x1, y1 is located in relation to the line. Now, we need to look at angle M. We have the hypotenuse of this right angle triangle. We know that the tan of M is the slope, as we saw in the previous example, and we can get the slope from the equation of the line. We just rearrange to make y the subject. If we do this, we get y equals minus a over b times x minus c over b. So now the line is in the form y equals mx plus c. When it's in this form, we know that this quantity here is the slope. By the way, the c in the slope-intercept form of a line, which is what this thing is called, is different from the constant. It's different from this constant here. Okay, we're using the same letter, but usually the values are different. As a matter of fact, when we write our line in this form, we get this. These are supposed to be the same. So obviously, in general, C stands for two different things. So that could be confusing. But anyway, we're only interested in the slope here. So tan of M, tan of the angle measured from the positive x-axis to the line, is the slope. To find d, we actually need the sine of M. Sine of M is d over the hypotenuse. So how do we get the sine of M from tan of M? Well, we can just use this ratio. Now, tan of M is actually positive, because M is an acute angle. So minus a over b will actually turn out to be positive. If we get the magnitude of minus a over b, of course we still have a positive quantity. We still have the slope of the line. We can imagine constructing a right angle triangle. Make the side opposite M the magnitude of A, make the side adjacent M the magnitude of B. We need to get the sine of M. To get the sine of M, we need the hypotenuse of this right angle triangle. So we use Pythagoras, square these and add them, and get the square root. But of course, if we square the magnitude of a quantity, it's just the same as squaring the quantity itself, because when we square any number, we get a positive number. So we don't have to have magnitudes in here. So now we can write down the sine of M. Sine of M is opposite over hypotenuse. And the sine of M has to come out to be positive, because M is an acute angle. And indeed it will. Mod A is obviously positive, and we're taking the positive square root. So the other way we get sine of M is by looking at this right angle triangle. Sine of M is the side opposite M, which is D, divided by the hypotenuse of this right angle triangle, which is this quantity here. And we just rearrange to get D. So we have to multiply mod A into this quantity. We can actually multiply A inside here and take the modulus of the result. Another way we could say that this is that the product of the moduli is the modulus of the product. Like, for example, suppose we're getting the modulus of minus 3 times, say, the modulus of 4. Well, that's just the same thing as the modulus of minus 3 times 4. Okay, the answer is 12 in each case. So that's what we did up here. Now, I'm assuming that the square root is the positive square root, so I only have the modulus lines on top. But of course, we can just get the modulus of the entire quantity. We can apply the same reasoning for a point on the other side of this line. Suppose we have a point here, and we're interested in getting the perpendicular distance to the line. Well, we'll be interested in the horizontal distance of the point to the line. Where is angle M going to appear? Well, this here is actually angle M. So we have a similar situation to the one we just did. Really a very similar approach. However, this quantity in here will be negative. Okay, see, the x value of this point is x1, and the x value of this point here will have this form. It'll be minus b over a y1 minus c over a, because we're talking about a point on the line. We get it in the same way that we got this. And if we work out x1 minus this, we'll get something negative. So if we're dealing with a point to the right of this line, this quantity in here is actually positive, because x1 is greater than this point. But for points to the left of this line, this quantity will be negative. This means that this quantity up here will be positive or negative depending on which side of the line we're measuring from. Because this quantity up here is just got by multiplying the quantity in here by A. So points on one side of the line will be positive or negative. They don't necessarily have to be positive, by the way. Points on this side could be negative. Depends on what value A is. Points on the other side of the line will have opposite sign for this quantity. But anyway, we'll be getting the magnitude, so ultimately we'll end up with a positive quantity. Now let's see the case where M is an obtuse angle. An obtuse angle is an angle between 90 and 180 degrees. If M is obtuse, then our line has a negative slope. So, to get the slope of the line, we get the tan of the angle measured anti-clockwise from the positive x-axis to the line. We know from rearranging the equation of the line that the slope is minus a over b. We saw that before. We just write the equation in slope-intercept form. Y equals mx plus c. The coefficient of x is minus a over b. This quantity must be negative for a line with negative slope. To find d, we need to know what this angle here is. I'm calling this angle k. Now in the last example, k was equal to m, but it's not the case here. As a matter of fact, k is equal to 180 degrees minus m. This angle here is actually K, but M and K add up to 180. And the two K's shown here are called alternate angles. We have the Z shape formed. We need to get tan K. Well, the tan of K is tan of 180 minus M. Now it's a fact that the tan of 180 minus any angle is minus tan of that angle. For example, if M was 120 degrees, then the tan of the angle next to it, which is 60 degrees, the tan of 120 and the tan of 60 are the same except for a sign difference. The tan of 120 would be negative because we're dealing with a line with negative slope, and the tan of this angle gives us the slope. So if M was 120 degrees, then the tan of 180 minus 120, or the tan of 60 degrees, would be positive, would be minus the tan of 120 degrees. So we have to get something positive, so we have to stick a minus sign here. K itself is an acute angle, so tan of K has to be positive. Anyway, we know what the tan of M is, so minus tan of M is just A over B, and it's going to be positive. So, knowing the tan of K, we can get the sine of K. Like before, we need the sine of this angle to find out what D is. So we just have a right angle triangle here, make the side opposite K A, or better, make it the magnitude of A, because A could be negative, and make the side adjacent to K the magnitude of B. Then we know from Pythagoras that hypotenuse is root A squared plus B squared. Now we can write down the sine of K. So we can make both, we can just get the magnitude of this, because A over B is positive anyway. So getting the magnitude won't change anything. So now we can write down the sine of K is the magnitude of A divided by root A squared plus B squared, just like before. Now we need this horizontal distance, but we've done that before. We just take the x value of this point and subtract the x value of this point. The quantity will actually be positive if we do that, because x1 is actually greater than the x value of this point. But in other situations, x1 is less than this value. If the point was on the other side of the line, then this quantity in here will be negative. But anyway, we get the magnitude of it, so we don't have any problems there. And what we do then is we use the fact that sine of K is opposite D over this quantity, opposite over hypotenuse. So just multiplying, then we get D equals the horizontal distance times the sine of K, just like before. So we get our result. So we just multiply A into this here. We get AX1 plus BY1 plus C. And of course we can take the magnitudes over the entire quantity, although it's normally assumed that the square root is the positive square root. But this is the usual way the result is written. Notice again that this quantity will have a certain sign, depending on whether the point is on one side of the line or the other side of the line. So this quantity changes sign. Basically because when we do this subtraction in here to get the length of the horizontal line, depends on whether x1 is greater than the x value of this point, minus b over a, y1 minus c over a, or whether x1 is less than the x value of this point. So points on one side of this line will give a positive value for this quantity, and points on the other side will give a negative value for this quantity. But of course we'll be getting the magnitude, so we'll end up with a positive quantity anyway.